Welcome to the School of Energy Resources Distinguished Speakers Series in conjunction with the College of Engineering and Physical Sciences and the Department of Energy and Petroleum Engineering. Our speaker today is Dr. Matthew Balhoff. He is the Department Chair and Professor in the Hildebrand Department of Petroleum and Geosystems Engineering at the University of Texas at Austin. Which he is really excited about the OU Texas football game this weekend, as am I. He is also the Lois, is that how you say that?
The
Lois and Richard Folger Leadership Chair, and holds the Bank of America Centennial Professorship in Petroleum Engineering. He co-leads the Industrial Affiliate Program on Chemical Enhanced Oil Recovery. Dr. Balhoff received his BS and PhD in chemical engineering from Louisiana State University. He became an SPE Distinguished Member in 2017 and is a winner of the 2022 SPE Lester Urin Award and 2014 SPE International Young Member Service Award and 2012 SPE International Teaching Fellow Award. He has 96 peer-reviewed publications, 39 conference papers in the areas of enhanced oil recovery, carbon storage, unconventional resource production, and fundamental processes of flow and transport through porous media. So thank you so much for being here today with us, and take it away.
Thank you for the invitation. So, yeah, I appreciate you you're having me here. Thank you for coming. I thought I'd start out with just a quick joke. So there was a professor near the end of his career, and the last thing he was going to do is this distinguished lecture tour where he went to a number of universities, a couple dozen, and gave this talk on all of his accomplishments. And he had done pretty well for himself and had hired a personal driver through all of this. And so he gave all these talks, and personal driver would always drop him off and then come watch the whole talk. And at his very last one, his driver says, you know, I've seen all of these. I've got it memorized. I've got it down. He's just like, I want a favor. Can I give your final talk? And the professor says, you know what, sure. He says, you can give the final talk. And so the professor sat down, and this driver gives the talk beautifully. He just nails it, gives the whole thing. The professor's just so happy, enthusiastic to see how good of a job he did. And then the moderator says, okay, well now I guess we got time for one question. And the driver panics. He didn't realize there were questions because he would always leave during the conclusion slide and go get the car to go pick him up. And so somebody in the audience asks a question, and he's nervous, but then he thinks quick on his feet, and he looks at the person asking the question. He says, you know, that's an easy question. That's such an easy question. I'm going to let my driver answer the question for you. As mentioned, I've been at the University of Texas at Austin, Petroleum and Geosystems Engineering since 2007. I'm now the department chair. I've been in that position for a couple months now. Just an FYI, it's not official yet, but I think we may have an open faculty position for an assistant professor. If that comes through, then you got some PhD students or postdocs that are interested in that. I hope you apply. I'm not sure the details of what we'd be looking for. Also, we're always looking for good, new PhD students and postdocs. I just hired a postdoc from here, Gideon. He just started with me last week, so I'm excited about that and continue to collaborate with the University of Wyoming. My talk is on new insights and mechanisms for chemical enhanced oil recovery using polymers. So a little bit of background on chemical EOR if you're not familiar with it. So normally we do water floods. At the end of the water flood, kind of a rule of thumb, maybe we've produced 1/3 of the oil in place. Another third is capillary trapped. And so that's due to interfacial tension forces. Some of it's trapped, and doesn't matter really what you do, how long you do a water flood or other kinds of certain floods, you can't recover that unless you reduce the interfacial tension. And then there's another third which is bypassed oil, and that's usually due to mobility control issues, right? So the goal of EOR is to get some of that remaining 2/3, right? Whether it be the capillary trapped oil or the bypassed oil. So surfactants are designed to reduce the interfacial tension, change the wettability, and get some of that capillary trapped oil. So surfactants are, you know, basically like detergents or soaps, right? So the same way you clean your dishes or you clean your clothes in the washing machine, same idea. It reduces that interfacial tension, so you're able to produce some of that oil. So that is intended to capture the capillary trapped oil. For the unswept oil, that's what we use polymers for. So these are usually aqueous-based polymers, and they're kind of thick fluids. I like to think of them as the consistency of like hair gel, right? I haven't used hair gel in a couple of decades, but that's basically what these polymers are like. So they're thick fluids, and they're intended to improve mobility control. So instead of having all this poor viscous fingering, you might get a more piston-like displacement. Key thing about polymers is it's intended to get that unswept oil, not the capillary trapped oil. Okay, and conventional wisdom and all of the theoretical analysis says that polymers are going to get the oil out sooner, but they're not going to get more of it, meaning they're not going to get the capillary trapped oil. What I hope to show today is that when polymers are designed and tailored with the right rheology, that they actually can recover some of that capillary trapped oil, or what I'll call residual oil, okay, or residual oil saturation. So that's what I hope to show, okay? And so where this came from was really about 15 years ago. I was talking to Professor Gary Pope in our department, and he showed me these experiments that were done a long time ago. And what he showed is that 2 experiments in 2 similar cores, a water flood and a polymer flood, gave very different residual oil saturations. And it appeared that this polymer flood, which appeared to have viscoelastic rheology properties, had a lower oil saturation. Now, it could have been because there were 2 different cores. It could have been that if you had done the water flood for another 100 pore volumes, that it would have eventually gotten down to that oil saturation of about 20%. So that really wouldn't have been capillary trapped oil. It would have been mobility control, which is what polymers are supposed to do, or it could have been something else. But nonetheless, it was interesting. And at the time, I was a pore scale modeler. I'd done all modeling up until this point, and I tried to tackle this problem from a modeling perspective, and I realized it was too hard to do at that time. And so one of the reasons there's 2 reasons I love to give this presentation. One of them is because this project turned me into an experimentalist. And the other is, as you'll see throughout this, is that we use lots of different tools and techniques and approaches to kind of try to solve the same problem. So that was the motivation for this. I'm going to introduce some dimensionless numbers. One you're probably familiar with if you work in petroleum engineering is mobility ratio. And so what you want is a mobility ratio of less than 1 to get good piston-like displacement. That's what the polymers do because they're more viscous. Mobility ratio above 1 gives that pore displacement, you know, kind of in that picture I had in the previous slide. So another important thing is a capillary desaturation curve. So what we're looking at here is sort of the kind of classic textbook view of a CDC, capillary desaturation curve. We have residual oil saturation versus the capillary number. Now, what we have here, so capillary number, a typical water flood might be right here, okay? It might be in this region. So if you increase the viscosity by maybe a factor of 10, like polymers do, you just push it over here. So that's why the conventional wisdom is that polymers aren't going to do anything for residual oil saturation. Now, if you reduce the interfacial tension by several orders of magnitude, like surfactants, then that's when you get this lower residual oil saturation. But the polymers shouldn't have any impact on residual oil. We'll see if that's true in our experiments. And so we're going to define this capillary number as the ratio of viscous to capillary forces. And so you can see things like, depending on how you define it, permeability, pressure drop, interfacial tension, length of the core, Or if you substitute Darcy's law, you got velocity and viscosity in there. So, but again, maybe we're going from here to here, from a water flood to a polymer flood. But some interesting things about our polymers is that they are non-Newtonian. Specifically, they're almost always shear thinning, and sometimes are viscoelastic. So here's a typical viscosity versus shear rate curve that you would get in a rheometer. And this is sort of covering it up, but there's this flat plateau over here. And the red curve is what I get in the rheometer. And the two match really well. And I'm sorry, but that label's covering it up, but they match really well there. And then you get the shear thinning behavior. If you do the same experiment, but you do it in a porous medium, in like a core, there's a deviation at some point, and you start to get this shear thickening sometimes. Okay, that shear thickening is usually attributed to viscoelasticity. More on viscoelasticity, we can measure the relative elasticity by doing an oscillatory shear experiment in a rheometer. This is the storage and loss homologous, G prime, G double prime, versus oscillatory shear. The intersection of these two is approximately the relaxation time of the fluid. So it's the inverse of that. So right here, it looks like it's about this is 1, that's 2, so I would call the relaxation time 1 divided by 2, or 0.5 seconds. Okay, so that's a relaxation time. To give you kind of an idea more about relaxation, remember, viscoelastic means it's got properties of a viscous liquid and an elastic solid. So a rubber band, okay, if you stretch it out, you would have to stretch it for a really, really, really long time in order for until you let it go for it not to remember its original shape, right? So I could hold it for a minute, let it go, and then it would go back to its original shape. It has a very large relaxation time, right? Maybe not infinity, but maybe close to it. It's clearly an elastic solid. A viscous liquid like water, if I pour water out of a cup, okay, it's going to immediately forget what its original shape was, right? It's not going to remember that it was in this 12-ounce can. So it's got a relaxation time of close to 0. So larger relaxation time, the more elastic it is, or I'll call it a viscoelastic fluid, okay? So it's got properties of both. And so some of our polymers have that. So I'm going to use a dimensionless number. The Hildebrand number was the ratio of the relaxation time to the resonance time. So tau is the relaxation time, V is the velocity, dP is like the grain diameter, okay? And so I'm going to talk a lot about this dimensionless Hildebrand number, and we can increase it by increasing the relaxation time, which is a function of things like salinity, polymer concentration, molecular weight, type of polymer, that kind of thing. But sometimes I'll also increase the velocity, and that will also increase the Hildebrand number. So my objective setting out was to go back and look at those experiments that Dr. Pope showed me and do a very careful set of experiments to determine if polymer elasticity actually affected residual oil saturation, which would go against decades of conventional wisdom on how polymers worked. So design those core flood experiments to isolate the effect of viscoelasticity, then develop new models relating SOR to Hildebrand number, determine if that was true, what were the mechanisms that were causing this, because it sort of goes against everything I teach in my water flooding class, and demonstrate the scalability by implementing into field scale reservoir simulators. So really, again, a lot of different techniques, a lot of different scales that we're going to do this. So let me start with some core scale experiments, some core floods we did. So this is a typical core flood apparatus. We did some with constant pressure using an argon cylinder. We did some at constant rate with a syringe pump. We had our chemical column where we included the polymer, our foot-long core, which was set vertically, and we had pressure taps along there so that we could be able to see where oil banks and stuff were. And that was kind of our core flood setup. We probably did, in total, 2 or 3 dozen experiments, right? And so I'm just going to show you a few. The experimental design, in general, was something like this. We would, well, first off, we would saturate it with brine or, water, salt water. So we'd saturate the flow with brine. Then we'd inject oil, sometimes low viscosity oil, sometimes high viscosity oil. And then we would have a starting point of maybe 85% oil saturation. So not too difficult from, a virgin reservoir, right? So then we would do our water flood, and we would do a brine flood. And, most of these experiments, maybe all of them, were ambient temperature and pressure, not necessarily reservoir conditions, but I was trying to answer some fundamental questions, and that served this purpose. We'd inject the brine, and then we would do many pore volumes, and we thought we were at residual oil saturation. But, some people might say, well, were you really, or did you have some unswept oil left behind, right? Remember I said that you can leave behind unswept oil or residual oil, and we wanted to be extra sure we were at residual oil saturation. So what I did is, in most of our experiments, we injected glycerin. So glycerin's a Newtonian fluid. It's aqueous, but it's got a high viscosity, so better mobility control. So we injected maybe a couple pore volumes of that, and then we were really, really sure that we were at residual oil saturation. Maybe we got 1, 2, or 3% oil out from this glycerin, but at that point, there's no reason to believe we're not at residual oil saturation. So then, we would never do that in a reservoir, but we're trying to answer some fundamental questions. Wanted to see if we could reduce residual oil. And at this point, if we're at that point, okay, so no more mobility control, we're not going to reduce the interfacial tension at all. So we do our polymer flood, same viscosity, so same mobility ratio. Remember that the dimensionless property M that I defined earlier. We would do that. And what we found, and what I hope to convince you, is that surprisingly, we almost always got a significant more amount of oil out, meaning that we reduced the residual oil saturation from the polymer flood. Even though we were already at residual oil saturation, even though we haven't increased the mobility ratio at all, we got this. And so let me show you an example of an experiment where we did that. Here's a case where we did a water flood. Deborah number is 0. It's an inelastic fluid. Okay, then we inject glycerol. In this case, we did get a couple percent out. Maybe there was some unswept oil. Okay, but then we got to this point and say, oh, okay, we're really at residual oil saturation. Then we did the polymer flood at a high Deborah number. We got 5% more oil out. And I'll point out that this was kind of on the low end. Most of our experiments were closer to about 10% on average. Very significant, right? We're not just talking about some noise. Very significant amount of oil that came out of here. And so we would see this many times. So to be extra sure that we're really getting residual oil saturation, we did this particular experiment in a CT scanner. So we have a medical CT scanner in our department. Sometimes the way we use this is that we do a scan either before and or after the experiment. This was sort of unique because we did the scans dynamically. We did them during the experiment. So we actually set up the experiment in there. So we've got this CT scanner. What we've got is a vertical positioning system. We got this X-ray beam that goes around. Okay, we got the core attached to the mount. That's that vertical. Okay, and then we've got our X-ray beam go around, and we can take scans around that cylindrical core, and so we can image that. Here's a picture of the actual CT scanner we used. This scanner is about 15 years old now. We just replaced it with a brand new CT scanner, but this is the one we used when we did these. So you can see the vertical positioning system. Here's the 1 foot long sandstone core that we did, and we did those images. And so what we found, this is that experiment I showed you. These are images along the core. So we did every centimeter, right? So there's 30 of them because it's a 30 centimeter long core. I'm just showing you 5. Okay, and I probably shouldn't be showing you this first and last one because they're literally the edges, and no matter what, you're going to get some sort of end effects. But let's pay attention to the middle 3 there. Okay, and the colors correspond to oil saturation. And so what we see is that this is at the end of the glycerin flood, and this is the end of the polymer flood. And what we're seeing is that you're actually seeing a reduction in some of those pixels of oil saturation. It's not just picking up unswept oil on those images, but reducing the residual oil saturation. You see this goes from 26 to 21%, for example. Okay, so that confirmed that these polymers are in fact reducing SOR, even though conventional wisdom says that it shouldn't. At least from traditional Buckley-Leverett theory. Okay, we've done dozens of these experiments to show this. We've varied the rock type, Bentheimer, Boise, Berea, high and low viscosity oils. This is one where we did a low viscosity oil. Because the mobility ratio is already so good, much less than 1, we didn't bother to do the glycerin flood, but we got an additional 11% oil out from the polymer flood. We varied the Deborah number by changing that relaxation time, meaning changing the salinity, concentration, molecular weight, but we also varied the injection velocity. And what we saw is, generally speaking, the higher the Deborah number, the lower the final SOR, right? So there was a correlation there. So more elastic fluid, the more oil you got out, okay? And so here was a collection of some of our data. This looks a lot like the capillary desaturation curve that I showed you before. So I call this an EDC, an elastic desaturation curve, because this is a plot of the ratio of residual oil saturation after a polymer flood to the water flood or the glycerin flood versus Deborah number on a logarithmic scale. A lot of scatter, okay? You can't do core floods without getting a lot of scatter because every rock's a little different, but generally a trend, higher Deborah number, lower SOR, and we developed kind of a simple empirical equation to describe that. So really anything above a Deborah number of 1 or certainly 10, you start to see a big effect, right? And you can control that Deborah number by maybe tailoring the rheology so it's got a maximum relaxation time, or probably what's less practical in the reservoir is to increase your velocity, because that Deborah number was relaxation time times velocity divided by some sort of length scale. So we did some more experiments, and most of the experiments I showed you before were done by a PhD student, Pong Pong Key, and then had a new master's student. He wanted to do some experiments, and so we had him do these and followed a very similar process as what Pong Pong did. So we did the water flood or the brine flood, then we did glycerol. In this case, you got a little bit of unswept oil. But then we did the polymer flood, had the same salinity as the other fluids, and had a high relaxation time. And he got 14% more oil out. He got 14% more oil out, which is fantastic, right? I mean, I showed you 5%. I told you sometimes closer to 10%. 14% was awesome. It was a little on the high end. And this was his first experiment, so me and his co-advisor, Gary Pope, said, well, we trust you. I'm sure you did the mass balance and calculated the oil right on the outward right part. Right? It's like, but let's do a tracer test as a verification that you got, that's really 14%, not like 9%. And so he says, sure. He says, look, what we want you to do is just change the salinity for part of that tracer test. And then, from that, you can do some math and figure out what your actual oil saturation difference is. So he comes back to us and he says, oh, I did your tracer test and I got 15% more oil out. We're like, what are you talking about? And he's like, yeah, I got 15% more oil out. And it's like, the final oil saturation is 7%. And we're like, there's no way. You didn't get 15% oil out by just changing the salinity to something higher. I mean, if you change it to lower, there's a salinity effect, but high, that nobody ever talks about a high salinity effect. And 7% final SOR from a polymer flood is really unheard of. I mean, from a surfactant flood, yeah, sure, but from a polymer flood. And so he said, look, for your first experiment, just do the whole thing over again. He does it all over again, gets similar results. So then we pull in Pong Pong and we said, look, you've been here for 4 years, you've been doing this. We want you to redo the experiment. We want you to do it by yourself. We want you to go into a different lab. We want you to do it on a different core and just follow his recipe and do that and tell us what you got. He comes back and he got something similar again. So we said, okay, there's something real here. And so what we found is that chasing this viscoelastic polymer flood with an inelastic polymer flood reduces SOR even more. Okay. If you reverse the order, then it doesn't do anything, at least the high salinity polymer flood. Although if you start like alternating these, we tried this, I mean, it's not particularly practical, but we kept on alternating it like for many pore volumes, and it kept on happening, but maybe with diminishing returns. So you get a little bit more oil each time, but eventually. So perhaps our most impactful and shocking discovery was that chasing the viscoelastic polymer with an inelastic polymer reduced it to very low levels. In this case, we got almost 30% more oil out from the glycerin flood, which is really amazing. We were able to repeat this many times. 3 different students were able to see this effect, which is really cool. So all this was very interesting. You know, we're seeing these macroscopic results. So that begs the question, why, right? Because, you know, if I'm teaching my water flooding class and teaching mobility control, Buckley-Leverett theory, none of that explains what we're seeing here. So then we went back to the pore scale and tried to observe some of these things. And for the last several years, we've been doing some microfluidics and micromodel work in our laboratory. So I won't go through all the details here, but we fabricate our own chips. We have a clean room. We create them out of glass. We can create almost any geometry we want to. We did some with little 1D channels, so microfluidic channels. So you can see here we've got these are like pores, and they're connected by like little throats. And let me show you some experiments we did with glycerin. So what you see here, this is an oil droplet, and we injected a certain flow rate, which corresponds to a certain capillary number. And we injected water or glycerin. You know, it didn't matter much. We saw the same sort of thing, is that if we increase the flow rate and the capillary number, this oil droplet would get smaller and smaller. Eventually, it would go all the way through. So the size of this oil droplet, we found experimentally, and we're actually able to derive it, was proportional number to the capillary number to the -1/3. It didn't matter if you had brine or glycerin or a surfactant solution, you know, or usually something else, it would follow this type of behavior. So I talked to my students and I said, well, you know, now let's do it with viscoelastic polymer. Maybe we'll get something different. Maybe the oil droplet will go through sooner and deviate from this theoretical model of the size of the droplet to the capillary number to the -1/3. What we got was, again, kind of surprising, almost the opposite of what we'd hypothesized. And this is the viscoelastic polymer, whether it be HPAM or polyethylene oxide. This droplet, what you can see here is if you got to a high enough velocity or capillary number or Hildebrand number, you start to see these oscillations or vibrations. And so it would never go through. Now, I thought that was kind of weird because I thought it was going to go through sooner at less of a flow rate or something. Now this is actually kind of blocking things. Okay, I don't know what's happening. One of my hypotheses is that what it's actually doing is acting as a conformance control agent. So maybe it's blocking up some pores and allowing oil to be pushed out, you know, in other places. It's still a working hypothesis, but something neat is happening here with a viscoelastic polymer that doesn't have with purely viscous liquids. So here is that droplet pore size versus capillary number to the -1/3. Here's our theoretical model. If you've got elastic effects, you start to see some deviation there, but kind of the opposite deviation that I had hypothesized. My students did a little bit of a force balance, and they derived a new expression which now has Hildebrand number in there. So the length, dimensionless length, is capillary number to the -1/3, 1 minus some constant times the Hildebrand number. What you're looking at here is, I mentioned that we had, this is distance versus time, so these are your periodic oscillations that we're seeing with those droplets. Here is amplitude versus flow rate, or Hildebrand number, and that's linear as well. So we created a kind of a semi-empirical model that says the amplitude is proportional to a Hildebrand number minus some sort of critical Hildebrand number. Okay, so this is some pore scale observations. We also did some lattice Boltzmann simulations. So Newtonian or viscous fluid versus a viscoelastic fluid. You see, in both cases, you get something not all that different than what we saw in the experiments. I mean, there's a lot of approximations and simplifications in the model, so not really a quantitative prediction, but qualitatively getting some very similar type behaviors. And then this is the distance of the oil droplet from the pore throat versus time. You see the Newtonian fluid eventually goes to zero, it goes through, but you get these vibrations or oscillations with the viscoelastic fluid. More Lattice-Boltzmann simulations. You can think of these little white X's being like a grain, and the little red droplets as being oil droplets. Newtonian fluid, zero Hildebrand number, they just stay trapped over there. You notice the streamlines are very symmetric, what you'd expect, but with the viscoelastic fluid, very chaotic, very turbulent. So there's something called viscoelastic turbulence. Not the same thing as turbulence at high Reynolds numbers, but very analogous to that, right? Because the Reynolds numbers were very close to zero in these cases. But that turbulence pulls out those oil droplets. And then here is some vorticity fields that my postdoc, Chiyu, was able to form. So another geometry, think of this as being like a dead-end pore. And so if you can see, what's happening here is that Newtonian fluid, you get these nice streamlines, nothing happens. Higher the Hildebrand number, these chaotic streamlines eventually pull out that oil droplet. So again, we're kind of developing some hypotheses. And even though I've been doing this for a while and maybe closing the book on some of this, I would still call them hypotheses. I don't think I've answered all the questions, but certainly some unique things are happening when the polymer is viscoelastic versus purely viscous. Here was one last geometry. This is called a pore doublet model. And so you've got, kind of a pore up there and a pore, this is the doublet. In this case, what you saw is that this oil droplet went through, but the bottom one was trapped. That's with an inelastic fluid. Then we tried a viscoelastic fluid. So this was maybe like a Maxwell model or something. Interestingly, the opposite oil droplet went through. Is it better? Is it worse? The same? I don't know. It's different. Okay. But what's neat is if I did that viscoelastic polymer flood and I got that, and then I chased it with an inelastic flood, then it pulls that out too. So maybe, just a hypothesis, but maybe that explains why when we chase the elastic polymer flood with an inelastic polymer flood, it got more oil out. Because that first one got this oil, and the second one got that oil, right? But if you use one or the other, you couldn't get both. So you're getting different kinds of oil in these types of things. So these were some Lattice-Boltzmann pore level simulations. Back to my microfluidics, and so I call microfluidics usually like single channel geometries. I call micromodels like microfluidic porous media on a chip. So most micromodels are relatively small. They're like, think of them like Lego chips, but they're maybe like a square centimeter. They're two-dimensional, but when we have our core flood, they're three-dimensional. They're very heterogeneous, obviously, like real rocks are heterogeneous. They have unique surface chemistry, right? So maybe calcite surface for carbonate rocks, and they're quite long. Okay, like our core floods were like a foot in length. So what we set out to do is could we create a micromodel that had, it's never going to be a replacement for core floods, but could it have some of these same properties? Could it be three-dimensional? And we created what we called a 2.5D micromodel, so it had three-dimensional properties. That's important because that allows you to have capillary snap-off and also continuity of the grain phase. Lots of micromodels are heterogeneous. A lot of times what they do is they use thin sections, but for the really, from like CT scans, but from what we're doing, larger scales, as I'll mention in a minute, that's really hard to do. So what we did is used a random network generator that was statistical, that was based on a real like micro CT thin section. We're able to code our micro models with calcite, so kind of control the surface chemistry. But then maybe one thing that I really like, and that's why I call it a core flood on a chip, is because it's the length of a core flood. So it's got this serpentine geometry, but it's like 1 foot in length. In fact, we've gone 1.5 feet in length. So by combining all of these things, I'm not going to call it a replacement for a core flood, but it's more core flood. It's more rock-like. Okay. So we did some experiments with this. So here's our chip. Okay, 10 centimeters by 10 centimeters, but 30 or 40 centimeters long because of the serpentine geometry. If you look in, you've got grains and throats and pores. It's very heterogeneous. We can do experiments just like we do in a core, so we can measure permeability because we've got pressure taps on either side. We inject at a certain velocity, so we can measure the permeability of our micromodel. We can also do other tests that we normally do, like tracer tests. And so what you have on the top is the micromodel, and the bottom would be one from a Berea core. So qualitatively, you're getting the same thing. And from this, you can determine porosity and heterogeneity and stuff like that. So not a polymer flood, but really cool image of a surfactant flood that I wanted to show you. So here is our core flood on a chip. On the left, I believe, is a water flood. And you can see that water, and you can see that leaving behind oil. Some of that might be unswept oil. A lot of it might be capillary trapped. But on the right is a surfactant flood. And you can visualize how well it is cleaning up that oil in that serpentine core flood on a chip. Okay, so I really like this because I think that this core flood on a chip could really be used as a screening tool for a lot of EOR type things, because these core floods are expensive, they're time consuming. It's not going to replace it, but we could do these with a very small footprint. We can do probably a dozen of them simultaneously. They don't take as long to start and finish. So maybe you do a few dozen of these experiments, the ones that are most promising, then you do the core flood on. Okay, and if you zoom in, you can actually see oil banks form. So this is a snapshot of that surfactant flood at a given time. Clearly, you've got oil buildup right over here. That's your oil bank. Okay, so using that core flood on a chip to look at the polymer flooding, my PhD student using DEW, she did some of these experiments. This is a brine flood followed by a glycerin flood and then a polymer flood. Nothing really surprising there, right? So you did the water flood, got to residual saturation, so injecting more mobile fluids didn't really do anything. Okay, but this was an inelastic polymer flood, so we kept the relaxation time low. We repeated that experiment by using a viscoelastic polymer, and kind of a theme here is I keep on getting surprising results. Okay, so in this case, this is going to really surprise you. The oil saturation went up. Now, how could that be? If I injected aqueous-based fluid, how did the oil saturation go up? I would have thought maybe it was going to go down or at least stay the same, but how you didn't put more oil into it. Remember that oil saturation is not by mass. That's a volume percentage. Okay, and so and we are determining this through image analysis. So we're counting pixels of where the oil is. So what we're really seeing here is an increase in volume percentage of pixels with oil in them. And what was happening, and I'll show more of this later, is that the oil is swelling. So by mass, there's not more oil in there. That's impossible. By volume, it's taking up more space because of this swelling, possibly with some of the brine kind of creating an emulsion with that. Okay, and so you actually saw an increase by volume, and then if we did an inelastic flood, then it started to pull out that oil. So you had deswelling, oil actually came out of the core. Very difficult, if not impossible, to measure a change in oil saturation by mass balance. the volumes are too small. We do everything by image analysis, but really cool results there. These are small scale images, so foot-long core, but we're zooming in to, say, a millimeter scale here. And you have this glycerol flood that happened first, then you had this elastic polymer flood, and if you could look closely enough, there are places, let me see if I did a circle, no, I didn't circle anything, but there are places where you can actually see the oil volume takes up more space than it did before. And then you do the second glycerol flood, all of a sudden those emulsions went away, some of this oil started to move downstream, we had a, we're starting to produce oil. Okay, so really neat stuff there. I'll finish up by going at so that was a very small scale. Now I'm going to go to a very large scale, at the reservoir scale. And so we did some reservoir simulation stuff with our chemical flooding reservoir simulator, UT Chem. We came up with a 5-spot pilot, which I show here. I'm going to be transparent. I chose geometry and conditions that I thought would give me more promising results, but I'm going to do some sensitivity analysis later to show that we get promising results no matter what. So 5-spot pattern, close well spacing, so 200 feet there, 50 feet thickness. We're injecting 1,000 barrels per day of water initially, then we'll follow that up with a polymer flood. We got a constant bottom hole pressure well. The polymer flood was done at 4,200 psi. 5 Darcy permeability, which is high but not uncommon for polymer floods. Heterogeneity, which I'll show a little bit more in a minute. Yeah, and that's what that. So we used a Dijkstra-Parsons coefficient and a correlation length to do that. Some key properties are in yellow. Focus on this number. The residual oil saturation is 30%. So from a water flood or an inelastic polymer flood, it doesn't matter if I injected an infinite number of pore volumes, I would never get below 30%, right? That's oil that's going to be left behind forever unless we do something to reduce that. I input that elastic desaturation curve empirical model that I developed from the experiments into the reservoir simulator. What we're looking at here is the Deborah number. Remember, I said that anything over 1 and certainly over 10 is impactful. And near the wellbores, where we have very high velocities, very high Deborah numbers. But even in the middle of the reservoir, somewhat high Deborah numbers. This is a cross-section between the producer and the injector, and you can kind of see what that is. That's Deborah number, which is correlated with residual oil saturation. So again, residual oil saturations as low as 15%. Remember, didn't expect to get lower than 30% from a water flood or a polymer flood, but this is the elastic polymer flood, which reduces SOR. Even in the middle of the reservoir, we're looking at 25%. So here's a plot of oil recovery versus pore volumes injected. Blue curve is just a water flood. Okay. Yellow curve is an inelastic polymer flood. This is just a regular polymer flood. It does what polymers are supposed to do, which is to get the oil out faster. You might not be able to tell, but if I were to inject 100 or 1,000 pore volumes of water, it would have eventually gotten up to this yellow curve. Not practical, but it would have gotten there. But with the elastic polymer, we got an additional 12% out, and neither of these would have ever gotten to that point. Okay, it's because of the elasticity, because of that model I put into the simulator. Here's a table with some of that sensitivity analysis. The base case was 12% additional oil, which is very, very significant. Okay, even just from a couple percentages would have been great. But I did some sensitivity analysis by varying the polymer concentration, salinity, and a variety of other things. And worst case scenario, I got an additional 3% out versus an inelastic polymer flood. Even that's significant. Okay. So I mentioned that I chose maybe optimal or very good conditions for this. That's what got me the 12%, but even not so good conditions was still effective. So some final thoughts are that the viscoelastic polymers do reduce residual oil saturation. That confirmed our hypothesis, but went against conventional wisdom of how polymer flooding works. We developed these new models, what I called an elastic desaturation curve, which relates SOR to Deborah number. We put those into the reservoir simulator. We found that not only does a viscoelastic polymer reduce residual oil saturation, but if you chase it with an inelastic polymer flood, it reduced SOR even more. We got some saturations down as low as less than 5%, which is unheard of for a polymer flood. That's what you get maybe with surfactant floods. We did these pore scale microfluidic micromodel experiments, as well as lattice-Boltzmann simulations, to provide some new insights, maybe new hypotheses as to why we're getting what we're getting. But I don't think all the answers. I don't have all the answers yet still, but we're definitely seeing some possible explanations for our macroscopic observations. And then simulations. I shouldn't call it a real pilot test. It was a it was a test pilot case in the simulator, but it showed that the viscoelastic polymer can recover incremental recovery at the field scale. Because one of the things I'd largely gotten is like, well, is this just a laboratory scale thing? Will you get to high enough velocities and Deborah numbers in the field to actually make a big enough of a difference? Our answer is that under the right conditions, yeah, you know, you can. It's not necessarily just a near wellbore thing. So with that, I just want to acknowledge all the many students and postdocs that have worked on this problem. Again, what I really like about giving this presentation is showing so many different aspects of things, so many different scales, experiments versus models, and that was only possible because I had such wonderful people on my team with different expertise that were able to contribute. Collaborated a lot with our faculty at UT Austin on this, and supported through our chemical EOR, JIP, and we also had some funding from King Fahd University of Petroleum and Minerals. And so more on that chemical EOR, JIP, I'd like to acknowledge those companies that supported this research. So with that, I'll open up to questions.
So now I forgot my question, but no, so this is a domain where there's clearly a lot of lab work and a lot of knowledge in terms of physics and chemistry and so on and so forth. There are a lot of publications about the use of data science, machine learning, and artificial intelligence, whatever you want to call it. So what do you think is what's your view on that? What's the potential contribution for this kind of tools like machine learning and so on and so forth in this domain?
Yeah,
sorry, I couldn't be more general than that.
Yeah, so the question is that how could data science and machine learning, artificial intelligence be used in some of this work? There's one really very specific, simple place where I've thought about that, and that was in the creation of those micromodels. So I mentioned how we wanted to create heterogeneous structures for a very large core, kind of a micromodel, something that was too big to just use a single micro CT scan, a thin section image. I think you could use machine learning to develop a heterogeneous micromodel that mimicked some of your thin section images. So that's one place where I've specifically thought about it. Otherwise, I'm not sure. Certainly with the reservoir simulation, when you talk about optimizing things, you could do several simulations and then use that to sort of predict maybe the optimal way to maximize your recovery.
Hi there. So it sounds like you haven't done field tests yet, but which is understandable. But have you guys run the economics of using that much chemical in the field relative to output?
Yeah. So question is basically about how to apply this in the field and whether or not it's economical and stuff. Some of the experiments we've done where we've just done a ton of pore volumes injected is not going to be economical, and that wasn't necessarily the purpose. It was to answer some fundamental questions. But certainly what we've seen was with just, so for example, this. This is pretty reasonable, and these were typical pore volumes injected to polymer. What is economical about this is that we're not really proposing to do anything different. We're saying to do a polymer flood, just ensure that the rheology is as elastic as possible, the red curve versus the yellow curve, because we do the yellow curve all the time. And then, what we're saying is just do the same thing, just try to tailor your rheology to optimize it. While we haven't done pilot tests and we haven't done it specifically, what we have seen is existing polymer floods that got better recoveries than the simulators and the engineers expected. Maybe it was elastic all along, right? Because some of these polymers are, most of these we didn't do anything special. We just used a HPAM polymer, and we tested the rheology, but it was already, so we may already be seeing this effect in the field. We just may not be realizing it. Otherwise, what it really involves is just being careful to tailor your rheology, choosing the right polymer concentration, molecular weight, type, salinity. Sometimes you don't have control over that because the reservoir might be high salinity, although you could do a salinity flush and inject low salinity polymer. But the other thing I proposed is working with chemists to graft new polymers that have ideal rheological properties. Now, back to your economics question, those polymers might be a little bit more expensive, but if you get 12% more oil out, it might be worth it.
Yeah, I think you kind of covered it. Thank you. Maybe I just missed it, but have you been able to conclusively determine any sort of like rheological tweaks to the polymers that conclusively have shown promising results in terms of increasing the recovery?
The relaxation time?
Yeah.
Yeah, so decreasing your salinity, increasing your concentration, increasing your molecular weight, all increase the relaxation time. Now, all those things also increase the viscosity, and what we really want is to increase the ratio of relaxation time to viscosity. So there is an optimum there, and I haven't done it yet. I've been trying to do it for years, is to do a lot of experimental work to figure out that space and to figure out that optimum. That might be another place for the data science and machine learning, do some experiments and try to optimize that, because but those are some of the variables that control that rheology.
Thank you.
Yeah.
Are you at least reducing the dependence on water by using the polymers?
Not necessarily, certainly not in this case, because instead of doing, you do the water flood, and then instead of continuing your water flood, you are using a water-based polymer, so it's about the same amount of water. Now, one thing that a lot of people have proposed, and I'm kind of a proponent of, is to forget the water flood altogether, go straight to a polymer flood. I think that might work, and I think it might be the best way to do things. It's a very difficult sell to managers, right? Because polymer floods are more expensive than water. You tell them, hey, we could just do a water flood and we'll get some oil out, and then we'll decide the next steps rather than jump into a polymer flood. But that might be in reality, that might be the most efficient way to do these floods and minimizing the amount of water you inject.
Thank you. Since I believe this work is directed to the process in water wet formations, so does your research happen to consider the polymer that has surface activity so that it can address the issues in the oil wet formation as well?
Yeah. So the question is that, was this work? This work looks like it's for water wet reservoirs, and would it apply for oil wet reservoirs? The majority of the experiments we did were water wet, but we did do some experiments. We published some of that work where we did a couple of core floods by changing the wettability to oil wet. I would say that I don't want to draw strong conclusions from that because there's only a couple, but it did look promising that even in oil wet cores, there was an effect here. I think that in our paper, we were careful to draw a strong conclusion based on a couple of core floods. But if there were more work done on this, I think that oil wet, mixed wet, intermediate wet cores would be something we would want to test more on.
Yeah, thank you so much for being here. So please join me one more time in thanking our speaker today. Here you go. It's a little gift. So thank you so much. Okay, and thank you. And great questions, and that concludes our Distinguished Speakers series for today. So thank you all so much for coming.